Welcome to this video tutorial on FPGA programming flow using Xilinx IAC and Misentenix ULK-1. My name is Alok and I will explain you how to use the Xilinx IAC tool to program the FPGAs in Misentenix Unified Learning Kit. I will be explaining you the flow step by step. The first step in this flow is to open the IAC tool. I will show you now how to open the IAC tool from the Ubuntu Linux terminal. In the Ubuntu Linux terminal, just type Xilinx and press enter key. It will start opening the Xilinx project navigator. Once the tool opens, you can close the Firefox window and the tip of the day. Now the next step is to create a new project. We will go back to the Xilinx tool and see how to create a new project. Go to File, New Project. Here we need to provide a name for the project and provide a location where we want to create the project. Let me browse to the directory where we have the RTL sources. So this is the directory where we have the RTL files and the constraints. So let me choose this directory to create the project, and let me give a name of the project like FPGA underscore demo. In the top level source type, we need not change the default setting since we are using HDL, verilog HDL as the source. We can keep the setting as it is. Click on next, and this is a very important menu where we are going to set some of the settings required for this project. In the product category, you can select all. In the family, make sure that you select the Spartan 6 device, since the device which we are using in Misentenix Unified Learning Kit is a Spartan 6 device, and the device should be XC6SLX45T. This information you can get it from the ULK board by reading the part number on the FPGA, or you can also get it from the ULK design document. In the package field, please select FGG484, and the speed grade you can select -2. Regarding the synthesis tools, we are going to use the Xilinx default XST synthesis tool, and for simulation we are going to use the Xilinx iSim simulator, so you need not change any settings here. In the preferred language field, Xilinx provides us the option of Verilog or vhdl language. For this particular demo, I am going to use Verilog files for the design, so I am selecting Verilog. In case you are using vhdl files, please select vhdl as the option. We need not change anything in this next setting, and if you are using vhdl, you can select whether you want vhdl 93 or vhdl 2000 or 2001 settings. For us, since we are using Verilog for this design, for this demo, right now this option doesn't matter. Let us now click on the next button, and it will show you a summary of whatever we have selected in the previous step. You can review it, and if everything is fine, you can click the finish button. If you want to make any change, you can click the back button and make the changes. Now once I click on the finish button, the project setting is ready, and we need to go to the next step, which is adding the RTL sources and the constraint file. To add the RTL sources, go to project, add source. Here browse to the directory where you have the RTL sources and the constraint files. For this particular demo, I have the RTL sources and the constraint files in two different directories. Let me select all the RTL files first. I have these files. We can select all of these by using the shift key. Here we can see in the association column there is an option to select all or simulation or implementation. In case the file is used only for simulation, for example a test bench file, you can select simulation so that during the implementation phase the Xilinx tool does not try to include that file. Since all the files I am using for this particular demo are used for implementation, I can either select implementation or I can just keep the default setting, which is all. Both are okay with this particular demo. Now click on OK, and now we need to add the constraint file. So go to project, add source, and browse to the directory where the constraint file is there. Xilinx uses a constraint file known as user constraint file or UCF file. Let us add this file. You can notice here the association for UCF file is automatically set to implementation, since UCF file is never used for simulation. Once we click on OK, we can see that the files have been displayed in the hierarchy window as per the design hierarchy, and if you double click on any of these files you can see the source code. For example, if I double click on the musical LED top.v, we can see the top level file of our design, which is a code for musical LED. We can see the IO ports, input, output, and the instantiation of the bottom level modules. If you double click on the UCF file, it will show you the UCF file here. We can see we have some timing constraints here. For example, the period is set for 100 MHz frequency, and we have the location constraint for some of the IO pins. Like this, you can browse the other source codes by double clicking on the corresponding file. Now we will go to the next step in the design flow, which is synthesis and implementation of the RTL code. To start the synthesis, click on the top level hierarchy, which is the musical LED top. Once you select the top level hierarchy, it will show you the different steps in the process. The first step is synthesize. To run the synthesis, you can just double click on the synthesize step and the tool will start synthesizing the design. It takes a few minutes to finish the synthesis process. Once the synthesis is done, you can see a message like process synthesize XST completed successfully, and if there are any errors after this step, you will see a red color cross like this, and if there are any warnings, you will see an exclamation mark like this. To see the warnings, you can click on the warnings tab and you can see there are a few warnings. Most of the time we can ignore those warnings, but it is always recommended to go through the warnings to make sure that we can ignore those warnings. If there are any errors, we cannot proceed to the next step, so you must fix the error before proceeding to the next step. Since we don't have any errors, we can proceed to the next step, which is implement design. In Xilinx design flow, the implement consists of 3 steps, which you can see by clicking on the plus symbol next to implement. It consists of translate, map, and place and route. In the translate step, the Xilinx tool will combine multiple netlists in case you have some IP cores or other netlists. In the map phase, the Xilinx tool will try to map the logical resources to the LUTs and other internal resources of the FPGA, and finally in the place and route stage the Xilinx tool will place the resources and will interconnect them using the FPGA's routing resources. So let us now try to implement the design by double clicking on the implement design phase, and it will start these steps one by one. First it will start the translate step. Once the translate is done, you can see there will be a tick button next to it. Then it will go to map, and then it will go to place and route. Let us wait for a few minutes until these 3 steps are over. During any of these steps, if any errors are there, it will show a red button next to it. If there are any warnings, you will see an exclamation mark. If there are no errors or warnings, you will see a green tick button next to it. Now we can see that all the 3 steps are done, and if you want to see the reports of these 3 steps, you can see the report summary on the right hand side. A very useful report is the design summary, where the design summary is shown in on HTML format. You can see the device utilization summary and the performance summary, and you can also see any of the detailed reports by just clicking on the corresponding step. For example, if you want the detailed report of synthesis step, you can just click on the synthesis report and it will open the text file, which is the detailed synthesis report. Similarly, if you want the map report or the place and route report, you can click on these hyperlinks. It will show you the corresponding file. So we have now completed the implementation phase in the flow, and the next step in the flow is to generate the programming file or the bit file.